Welcome back to my YouTube channel. I, Dr. Prakash Verma, welcome you all in the series of the modern control theory, or you can say the modern control system. Today in this video, we will try to understand the another part of the controller design based on the feedback controller part, feedback controller design uh, on basis of the pole placement system or the pole placement design. So today we will cover the Ackermann formula for the controller design, for the, you can say, the feedback controller design, right? Feedback controller design, controller design based on the principle of pole placement design, right? Pole placement design. This is the last part of your pole placement design course, post placement type topic. Okay. So in the previous lecture, we have already covered the, the matching coefficient, how the pole placement, how the feedback controller design may be designed using the method of matching coefficients. We have already covered one numerical, and then after covering this, we have also studied the design of the feedback controller using the transformation to controllable canonical form or CCF. And then as you know that in the case of the controller design using the controllable canonical form by transformation matrix, or you can say the feedback controller using the matching coefficient, you know the limitation of this concept. However, you don't know the limitation of the concept of the controllable canonical form. Since the procedure of adopting or procedure to solve the problem using this theory is more complex, because you have to find the different parameters like m into mz inverse. You have to find out the you can say the k into kz p inverse, okay, in order to find out the gain. First of all, you have to target is to find out the kz into p inverse, where in order to the find out the kz, as you know, the you can find out the kz using the formula p of p inverse. P inverse is equals to nothing but p is equals to m into mz inverse. So you have to find all these parameters when you move towards in order to solve this type of problem, right? So to resolve such type of complexity, to avoid such type of complexity, we are now using the Ackermann formula. So before proceeding the Ackermann formula, I again referring to, I try to appeal for to my students. Uh, if you don't have go through the previous topics of the modern control system, it is my request to go through, because only when you can connect this new topic, when you have covered all the concept was clear, right? So it is my request to please go through and okay. So now I am going to start the Ackermann formula. So as we have highlighted the in the case of the matching coefficient, or in the case of the CCF transformation method, you have to adopt a tedious or complex formula. However, in the case of Acker formula, just you have to apply the single formula and the you can find out the feedback control gain matrix. Okay, so it is the most easiest method based on the Calais-Hamilton theorem. So this method is based on the Calais-Hamilton theorem. Calais-Hamilton theorem, and the beauty of Calais-Hamilton theorem is, it repeats or every square matrix satisfies its own characteristic equation. The beauty of the Calais-Hamilton theorem is the every square matrix satisfies its own characteristic equation. Based on this theorem, Based on theorem, we will try to develop the Ackermann formula for the control design. Okay, so we are starting. So the feedback, you can say that the feedback controller gain, that is the K matrix. Okay, the K matrix, the feedback controller gain matrix K can be simply find out, right? Can be simply computed or obtained directly, right? Directly using Ackermann formula, right? Using Ackermann formula. So this avoid the complexity. Okay, so simple. Okay, let's say now starting the theory how the formula is going to develop. In order to that, let us consider we have a third order system. Let us consider we have a third order system which dynamic is third order system which dynamics or which state model is given by let's say x dot is equals to ax plus bu, however y is equals to let us see x. Okay, and you know that in any form of the controller design you have to check the controllability. If the system is not controllable, it means you are not able to drive the controller design. Okay, when you are not able to design the controller, okay, feedback controller. Okay, so first it is a necessary condition, the controllability matrix. You have to check the controllabilities of the system. So for that purpose we have to design the first model matrix, that's the controllability matrix M, and it's nothing for this, since it's a third order system, so you can write b a b a square b, and it should be the since it is the since it should be the controllable, it means the M matrix has full rank. Okay, it should be the full rank, so that the system is completely controllable. So first part we have to ensure the controllability part, then only you can proceed. If the system is not controllable, then it means you are not able to design the control level. You can say the Ackermann Formula, and or you can say any controller design you can't do. You can't be able to design, right? So with a state feedback, let the equation be क्या हो जाएगा? Let the equation become, the equation will modify, and you know a minus bk, right? A minus bk x plus bf into r. We already have covered this topic, how this will be designed in the case of the principle of the feedback controller design, right? If you have not gone, please, I am requesting once again, go through it, right? Okay, because you have to put how it will come. U c equal to u equal to fr minus kx from the block diagram that I have drawn in the earlier picture. Okay, that is the state feedback controller. I have already gone state feedback controller. You can go through that video also, in which we have covered the principle of feedback controller design. Okay, or the pole placement design, right? Or you can say the method of matching coefficient, right? So based on that principle, you have to design. You have already designed the x dot is equals to a minus bk x plus bf into r. So this is the modified state matrix, and this is the input matrix. Okay, now let us consider k, the feedback controller gain. Let the since it's a third order system, then no problem. Let the feedback controller gain matrix be k equal to k0, k1, k2, since it is the third order system, right? And now the system matrix modified, and the system matrix becomes what? System matrix becomes very simple, AF, and this AF is equal to nothing but the A minus BK. A minus BK. So the characteristic equation, so you can say the characteristic equation with state feedback, because your now characteristic equation also changed. That is not Si minus A. Now it is your Si minus AF. The characteristic equation becomes Si minus A because system dynamic system matrix will change. Okay, system matrix is changed. Therefore, Si minus AF is a characteristic equation. And this is nothing but, the Si minus AF is equals to, you can say, the Si minus A minus Bk equal to 0. Right? Si minus A equal to 0. Okay. Now, so this is a very simple concept. Let us consider this yield a third order system. Let the characteristic equation, the final characteristic equation will come into the third order system. We consider the third order system we have considered. So this will let us consider gives a third order polynomial. The form is like, let's say x cube is plus alpha 2s square plus alpha 1s plus alpha naught equal to 0. Okay. Now the Calais-Hamilton theorem. Now the Calais-Hamilton theorem. Now we are trying to apply the Calais-Hamilton theorem, and you know Calais-Hamilton theorem states that already covered, states that every square matrix satisfy its own characteristic equation. So this is the point. So based on this principle, based on this theory, you can write as phi AF equal to, it will repeat because system dynamics, there is a square matrix. AF is a square matrix, so you can say simply AFQ plus alpha 2 AF square plus alpha 1 AF plus alpha naught I equal to 0, where AF is equals to A minus BK. Right? Now, since AF is equals to A minus BK, then what is AF square? AF square is A minus BK into A minus BK, and it will be the A square minus ABK minus BK into A minus BK, right? A minus BK, and it will give A square minus ABK into minus BK into A minus BK is nothing but the AF. Okay. And what about the AFQ? Because you need this value AFQ, this value AF square, this value AF. Now we are going to put this value. So AFQ becomes A minus BK into A square minus ABK minus B into K into AF, right? And when you solve this equation, you will get AQ minus A square BK minus ABKF, okay, A minus ABKF minus of BK into same term A square minus ABK minus BKAF, right? And it is nothing but the AQ minus A square BK minus ABKAF minus of BK into this term is nothing but again the AF square. So AF square, right? Now try to put this value into the phi AF, this equation, okay? So now put, and this term is here, right? So put this value phi AF is equals to AFQ plus alpha 2 AF square plus alpha 1 AF plus I. Okay. Now put all this value So when you put this value, you know, AQ minus of A square BK minus of ABKAF minus of BKAF square. So this will come as a FQ plus alpha 2 A square minus ABK. I am taking the value here, this value, ABK minus of BKF, right? BKF. Okay, and plus then alpha 1 and alpha 1 AF, and AF is nothing but the A minus BK and alpha naught I. Alpha naught I equal to 0. Alpha naught I equal to 0. So this is simple. When you rearrange this equation, okay, try to rearrange this equation, it become AQ minus AQ plus alpha 2A square plus alpha 1A plus alpha naught I become what? A square BK A square BK plus ABKF plus BKF square, okay, plus alpha 2 ABK plus BKAF plus alpha 1 BK, right? So this is the case. Okay, so this we can write, okay, AQ plus alpha 2A square plus alpha 1A plus alpha naught I is here, and all the term negative terms will send to the right hand side, and that term is written here. Okay, so when you again solve this equation, this can be written as a phi A, okay, because you know the every square matrix repeats itself, so based on this, A square BK plus ABKAF, okay, plus BKAF square, okay, plus alpha 2 ABK plus BKAF plus alpha 1 BK, okay. So this is the term, and when you rearrange it again, you can take the common alpha 2 is, you can also write like this, B, when you take the common from this side, B, then it become alpha 2k, okay, from this value, alpha 2k AF, okay. When you take from this B common, so alpha 1 k plus when you take the k b from this value, then it will come KAF square, okay. Then plus take AB as a common, because we need BAB A square B, right? BAB A square B type term. So first we have taken the common B, then we have taken the common AB, then we will take the A square B. When you take the AB from the remaining term, then it will give the alpha 2k, then this term, right? And then KAF, that means AB, this term. From this term, you can take KAF, right? KAF, okay? And now take the value A square B, right? a square b, then the remaining term is nothing but the this value. So ab ये बन जाएगा k, right? So ultimately you can write like this phi a, this phi a may be written as B matrix, AB matrix, A square B matrix into alpha 2 KAF plus alpha 1 K plus KAF square, then alpha 2 K plus KAF plus K. Ultimate goal is to find the value of K, as you know. So when it will come, when you multiply this value, when this term will 0, the dominancy of this term will 0. And how it will come 0? So pre-multiply both sides by a matrix, 0 0 1. So when you multiply by 0 0 1 0 0 1, okay, and this is nothing, this is nothing but the M matrix. Okay, this is nothing but the M matrix, and when you carry out this side, then it becomes M inverse, right? And that is the phi A. Okay, so phi A, and you have already multiplied with the 0 0 1, then it will come like this, that is alpha 2 KAF plus alpha 1 K, right, plus KAF square alpha 2K plus KAF and K. Third column, third element of this column is this one. So once you multiply it, you will got simply K, and it is a target. It means the value of K, if you want to find out, the final value of K, simple value of K is nothing but the 0 0 1. You have to multiply it with the model matrix inverse, and then the characteristic of the phi A. If you want to find out, if you want in general term, you can say in general for an nth system, nth order system, it will very become easier. Nth order system, then k is nothing but 0 0 0 up to the last term, and last term will be 1. Then find out the m inverse and multiply with the phi a, it will give the k. Okay, so this is all about the derivation of the Ackermann formula for the controller design. Now times to verify with one example. Let us, I am taking the previous example that I already have solved. Let's say x dot is equals to minus 3 1 0 minus 2 into x. This is the dynamics of an electric system. 0 1, this is a second 2 by 2 matrix, right? So k is equals to simply, we have to take the value k0 k1, and y is equals to, we have to take just, let's say, given 2 1 into x. Okay, so first criteria is nothing but you have to check the model matrix controllability, right? So simple BAB. So BAB is nothing but B matrix is already given 0 1. When you find out the AB, okay, it will yield 1 minus 2. So when you find, this is the second order, second, you can say rank is 2, or you can say find the determinant is non-zero, then it means it is the completely controllable. It is completely controllable level system, which means you are able to design the controller. You need M inverse because in the final value k, the value of k is defined as 0 0 1 matrix, and M inverse, okay, M inverse, then phi A. Okay, so this is all about this one. So M inverse you have to find. So you can find out simply M inverse. M inverse is nothing but the okay. 2 1 1 0. It will be the the matrix M minus 1, M inverse. Now also given the desired matrix that is not mentioned in the problem. I left that point, but it is given, and I am trying to mention that value. Your specification is given. Design a feedback controller. Design a feedback controller. Okay, we already done that. Places the closed loop pole at s is equals to minus 3 plus minus 3j plus minus 3j, right? So based on this characteristic equation or desired specification, you may develop the characteristic equation, and the characteristic equation is s plus 3 whole square plus 3 square, that is the s square plus 6s plus 18 equal to 0, or equal to s square plus alpha 1s plus alpha naught. Okay, so this is the characteristic equation alpha 1. So alpha 1 is here 6, and alpha 2 alpha naught is equals to 18. Remember, it will need. Okay, now next is the phi a. So simple phi a is a square plus, since it is second order system, alpha 2a plus alpha naught, sorry, alpha 1a plus alpha naught I. This is the characteristic equation. So a square, you can find out the a square, since a is given minus 3 1 0 minus 2. A is given minus 3 1 0 minus 2. Based on this value, you can find out the a square. A square will come 9 minus 5 0 4. Okay, and put this value to 5 in order to calculate the phi a. So 9 minus 5 0 4 plus alpha 1 is 6. A is nothing but the minus 3 1 0 minus 2, and then alpha naught is 18. I is means I nothing but the 1 0 0 1. Based on this, you can calculate this value. So 9 1 0 10. Okay, so it will come. So K matrix is nothing, or you have already calculated the phi, you have calculated the M inverse. So K is nothing but the 0 G 1. Okay, since it is second order matrix, M inverse phi A. Okay, so 0 1, M inverse is 2 1, sorry, 2 1 1 0, and phi A is 9 1 0 10. Calculate this, it will come 9. It will come 9 1, right? So this is the answer. So this is all about Ackermann. Okay, so you can design the controller with the help of Ackermann more easily approach. Okay, so it is one of the easiest approach by which you can design the controller. If you have any doubt, just you can leave the message on or comment, just to comment on the comment, so that I can try to resolve your problem. So thank you very much. In the next problem, in the next class, we will try to cover the state observer. We will start the new topic, that is the state observer. Thank you.